Period 7 element. A period 7 element is one of the chemical elements in the 7th row of the periodic table of the chemical elements. The periodic table is laid out in rows to illustrate recurring trends in the chemical behavior of the elements as their atomic number increases. A new row is begun when chemical behavior begins to repeat, meaning that elements with similar behavior fall into the same vertical columns. The 7th period contains 32 elements, tied for the most with period 6, beginning with francium and ending with oganesson, the heaviest element currently discovered. As a rule, period 7 elements fill their 7s shells first, then their 5f, 6d, and 7p shells, in that order. However, there are exceptions, such as plutonium. All elements of period 7 are radioactive. This period contains the actinides, which contains the heaviest naturally occurring element, plutonium. Subsequent elements must be synthesized artificially. Whilst the first 5 of these are now available in macroscopic quantities, most are extremely rare, having only been prepared in microgram amounts or less. The later, trans-actinide elements have only been identified in laboratories in batches of a few atoms at a time. Although the rarity of many of these elements means that experimental results are not very extensive, their periodic and group trends are less well defined than other periods. Whilst francium and radium do show typical properties of their respective groups, actinides display a much greater variety of behavior and oxidation states than the lanthanides. These peculiarities are due to a variety of factors, including a large degree of spin-orbit coupling and relativistic effects, ultimately caused by the very high positive electrical charge from their massive atomic nuclei. Prediction. Exception to the Madelung rule. Francium and radium make up the S-block elements of the 7th period. Francium is a chemical element with symbol Fr and atomic number 87. It was formerly known as EKA cesium and actinium K. It is one of the 2 least electronegative elements, the other being cesium. Francium is a highly radioactive metal that decays into astidine, radium, and radon. As an alkali metal, it has 1 valence electron. Francium was discovered by Marguerite Curie in France in 1939. It was the last element discovered in nature, rather than by synthesis. Outside the laboratory, francium is extremely rare, with trace amounts found in uranium and thorium ores, where the isotope francium-223 continually forms and decays. As little as 20-30 G exists at any given time throughout the Earth's crust. The other isotopes are entirely synthetic. The largest amount produced in the laboratory was a cluster of more than 300,000 atoms. Radium is a chemical element with atomic number 88, represented by the symbol Ra. Radium is an almost pure white alkaline earth metal, but it readily oxidizes on exposure to air, becoming black in color. All isotopes of radium are highly radioactive, with the most stable isotope being radium-226, which has a half-life of 1,601 years and decays into radon gas. Because of such instability, radium is luminescent, glowing a faint blue. Radium, in the form of radium chloride, was discovered by Marie Sklodowska-Curie and Pierre Curie in 1898. They extracted the radium compound from uraninite and published the discovery at the French Academy of Sciences 5 days later. Radium was isolated in its metallic state by Marie Curie and André-Louis Debierne through the electrolysis of radium chloride in 1910. Since its discovery, it has given names such as radium A and radium C2 to several isotopes of other elements that are decay products of radium-226. In nature, radium is found in uranium ores in trace amounts as small as 1/7 of a gram per ton of uraninite. Radium is not necessary for living organisms, and adverse health effects are likely when it is incorporated into biochemical processes because of its radioactivity and chemical reactivity. The actinide or actinoid series encompasses the 15 metallic chemical elements with atomic numbers from 89 to 103, actinium through lawrencium. The actinide series derives its name from the group 3-element actinium. All but one of the actinides are F-block elements, corresponding to the filling of the 5F electron shell. Actinium, a D-block element, is also generally considered an actinide. In comparison with the lanthanides, also mostly F-block elements, the actinides show much more variable valence. Of the actinides, thorium and uranium occur naturally in substantial, primordial, quantities. The radioactive decay of uranium produces transient amounts of actinium, protactinium, and plutonium, and atoms of neptunium are occasionally produced from transmutation reactions in uranium ores. The other actinides are purely synthetic elements, although the first 6 actinides after plutonium would have been produced during the Oklo phenomenon, and curium almost certainly previously existed in nature as an extinct radionuclide. Nuclear weapons tests have released at least 6 actinides heavier than plutonium into the environment. Analysis of debris from a 1952 hydrogen bomb explosion showed the presence of americium, curium, berkelium, californium, einsteinium, and fermium. All actinides are radioactive and release energy upon radioactive decay. Naturally occurring uranium and thorium, and synthetically produced plutonium are the most abundant actinides on Earth. These are used in nuclear reactors and nuclear weapons. Uranium and thorium also have diverse current or historical uses, and americium is used in the ionization chambers of most modern smoke detectors. In presentations of the periodic table, the lanthanides and the actinides are customarily shown as 2 additional rows below the main body of the table, with placeholders or else a selected single element of each series shown in a single cell of the main table, between barium and hafnium, and radium and rutherfordium, respectively. This convention is entirely a matter of aesthetics and formatting practicality. A rarely used wide-formatted periodic table shows the lanthanide and actinide series in their proper columns, as parts of the table's 6th and 7th rows. Transactinide elements are the chemical elements with atomic numbers greater than those of the actinides, the heaviest of which is lawrencium. All transactinides of period 7 have been discovered, up to oganesson. Transactinide elements are also transuranic elements, that is, have an atomic number greater than that of uranium, an actinide. The further distinction of having an atomic number greater than the actinides is significant in several ways. Transactinides are radioactive and have only been obtained synthetically in laboratories. None of these elements has ever been collected in a macroscopic sample. Transactinide elements are all named after nuclear physicists and chemists or important locations involved in the synthesis of the elements. Chemistry Nobel Prize winner Glenn T. Seaborg, who first proposed the actinide concept which led to the acceptance of the actinide series, also proposed the existence of a transactinide series ranging from element 104 to 121 and a superactinide series approximately spanning elements 122 to 153. The transactinide Seaborgium is named in his honor. IUPAC defines an element to exist if its lifetime is longer than 1014 seconds, the time needed for the nucleus to form an electronic cloud.